Okay, so I just want to mention these circuit construction for the control unitary. This is one qubit, and if this can be decomposed into AX, B, X, C, and A, B, C multiplied to 1, and this control unitary can be constructed like this.
There's chat messages.
Wait, that?
There's chat messages.
There's chat messages. Okay. Yeah, we connected. Yeah. Right. So if you see that, you probably see this. If you have not seen it, that means you didn't go to the class, right? So, but most likely you don't need to do that on your own. In this, you just use the software. Okay, and you can prove that, but we won't do that here. Okay, and there's also how to implement arbitrary rotation, right? So we can do the SU2, and SU2 you can actually use the Euler angle. And remember we have these rotation, right? The two axes, and you want to align them, and you can do the three step, right? 3 step to align them. Okay, so it's indicated here. So I won't go through them, but it's indicated here. You do the RZ, little z, with alpha, so align this to n, and then respect to n, align with beta angle, rotation respect to that, align the z axis, and then one z axis, you just need to align xy. Okay, but these are in terms of axes that are not really fixed, like n, you don't really know n is what by the intersection you can find it, but you want to convert to a fixed axis, for example, x, y, z, right? And then you get these two. You also learn this in quantum mechanics. So, and yeah, this is how you construct arbitrary unitary. And then you can single qubit unitary, and then you can do the control unitary, right? So this shows that you can do arbitrary 2-qubit unitary control unitary in this form and use arbitrary single qubit. And we talk about universality. You have arbitrary 1-qubit gate. You have any, okay, you have already control now, so it's universal. So in principle, then you get any unitary you can decompose into these basis gates. Okay. And this ABC you can find from this by choosing these expression. This. Okay. Oh, maybe I should use cursor on my computer because then they get recorded. Okay. Yeah, and then you could also do the 3-qubit, right? In 3-qubit, you can decompose this way. For arbitrary qubit control unitary, it's getting harder and harder without ancilla. But if you use ancilla, it's slightly easier. Okay, this is the Toffoli gate decomposition that you work out in your homework, right? Anyone still remember the homework? Okay, so I'm not going to do that. Okay. So as I said, if you don't use ancilla, it's going to be very difficult for control arbitrary rotation, multiple control. But this from Nielsen Tron, if you have additional qubits that allow you to do this more efficiently, you just use Toffoli gate. Okay. So if you have more than 2-qubit control, then this how you do that. So it is a very nice pattern. Yeah. So I'm basically saying that in principle you can write any circuit in terms of the basic gate. Yeah. Okay. The Qiskit has a circuit library. We saw these simple gate X, H, and CX, right? And we also see quite a few others gates. Yeah, they have a library of standard circuit and common circuit. There's a documentation. So standard circuit, we already see this. They also quantum Fourier transform. We also show that. There's some other variational ansatz. So we're going to talk about variational circuit, but basically they parameterize the gate using some parameter, some rotation angle you don't specify, or you allow it to change later, and then you want to optimize. So that may be the circuit output state that give rise to the lowest energy of your Hamiltonian, or some optimization problem. Yeah, so they already construct these. In the past, you have to write this on your own, and they have developed these parameterized circuit for chemistry, the combinatorial problem. For example, in this later one, you have these QLOA ansatz. We'll talk about QLOA, but we mentioned QLOA in the QRS course. Yeah. So we'll go to the documentation. And there's some benchmark circuit. There's something called quantum volume that IBM developed just to characterize overall how good the machine is. And other benchmark. So let me go to the documentation. Yeah, let me go to documentation. Did I just ignore that? Go to here. This is the documentation. Oh, yeah, this is the documentation. Let's see. This page have many gates. Standard gate. I basically download a notebook and I upload it to the Brightspace. You can download that first notebook if you can download that. We can play with these. So you can also scroll to the left. There are a lot of gates that will show up. Scroll up. Construct circuit, etc. Okay, so from this you can there are links, go to other standard gates, and there are other, you'll see standard gate, they even have AND gate or gate. So these 3 control gate square root of x. So all these gates are already defined in the circuit library. Okay, right. Any gate probably you can think of, they already have it here. Like I mentioned, there's these ansatz. You can just directly use it. QFT. Okay, the basic gate, easy gate. Yeah. So maybe we just look at the code. If you download from the Brightspace, this is the documentation. Is this the one? Is this the one that I opened? Yeah. So you can play with this. So the standard gate. So for example, here they import a Hadamard gate. It's called H gate. So you need to import from this. But the Hadamard gate we use circuit.h. It's already included in the quantum circuit. But this is a different. They are not the same, but the function. the functionality is the same. But the way to use it is slightly different. For example, you say a Hadamard gate is this Hadamard gate. And what you do is you append. For example, you use QC.append. You append that gate to the circuit. So you don't write QC.hgate. It's different. This is different. And you need to specify which qubit, 0, right? You could specify a set, a list. And this multiple control X gate, you call this is a class, right? This is class. And 3 would indicate that you have 3 control bit. And so in total, it's a 4-qubit gate. So you see that here, right? So you append that. So this will be a Hadamard gate and then control NOT gate. Okay. So you can play with that. You can even import other things and then append. For example, I don't know what gate you want. Which where is that previous? Okay, it's here. Standard gate. Okay. This is from that. But we can find other gate to append. Okay. Okay, so let's do something. Okay, what is this? This is a control swap gate. Okay. Control swap gate. Yeah, so you would import control swap C swap gate. Okay, we can do this, for example. Well, this is time you can just play with the code. I'm just saying. I'm going to okay, I'm going to import this from Qiskit Circuit Library, import C swap gate, C swap equal to C swap gate, and then let's say QC append C swap. Well, actually, you could just, without writing the name, without assigning to that, and just directly say C swap. I think that was what I did next. C swap, and then we'll probably need to say which qubit. Maybe let's say 1, 2, 3, and then let's throw that. Hopefully it will work. Right, so I'm doing the C swap here. Okay. So as I said, you don't need to assign this to a variable. You just directly use it. That would also be fine. Yeah. So I modified this because it's not on the original documentation. They try to provide the most concise information, but you play with that by modifying. Okay. Any questions on this? Yeah, you can see the standard gate, yeah, from that link. Yeah. And n local gate. This is, as I mentioned, this is that's going to be used for the variational answer. So they have, for example, from this library you import two local, and all the structure will be two local. So we probably will cover this more in variational ansatz. So two local would be this kind of structure. So this circuit has 3 qubit. Two local means that it's always like 2 qubit or 1 qubit gate. So it would, this is already they designed this way, so they would have Rx, and then two local. If you probably don't specify, maybe the default will be auto. I'm not sure. You need to look at the documentation when you are using this. So we only need to have the overall picture. It's fine. And when you need to use it, you just need to look up the documentation. Okay. So you see these are only Rx and CZ because you specify the gate here. Rotation gate is Rx, right? RZ, right? And you draw this, right? You see this. And you notice that there are labeled datas here. These are the parameters that you can change. So far, in this circuit, at this point, it's really just symbolic. It's a placeholder that hold the data. How many you have? You have 12, right? And you can, okay, let me execute this line. And you can say local that parameter will show, you get a list of parameters. Okay. Right. Then you may ask, how do I use it? You use it by assign the parameter. So for example, if you have a list of numbers, here, okay, it used this function called assign parameter. You just assign a list of numbers, then it would have put into the circuit with the value that you specify. So for example, here it's using okay, P for 0, 0 for P in this parameter list. It would assign everything to be 0, right? So what we could do is we could assign, say P is P. I assign 0, 1, 2, 3 up to 11, right? You saw the original, it was, no, I shouldn't say P for P. Let me just say for J, for JP in enumerate. We learned this, right? Enumerate is giving the list and also giving the value. Let me see if it works. Just testing my thumb. Right, it works, right? So enumerate is, you go to the list and enumerate give you the order with the number 0, 1, 2. So I basically assign 0, 1, 2, 3 up to 11. Right. Okay. And in variational ansatz, you would change these parameters and see the energy and keep adjusting them. Okay. There are also things that designed for machine learning, they call Z features. So I'm not going, maybe not too much detail, but just go through the code. You have a list of 3 numbers. These are the things that you want to encode into the circuit. For example, you have a classical data you want to load into circuit, or even classical machine learning, you need to load these vectors. And you need to map into quantum circuit, right? So this, they design these called feature map. Okay. And then you can assign the value to the features. Okay. So yeah, you see that this is a feature, but it's just a symbol. Z feature is encoding these 0.2, 0.4, 0.8 into the circuit. But what really is inside that is you can just use decompose and see what it comes out. It's really encoding the 0 in here, 0.2, maybe it multiplied by 2, right? They multiply by 2. And so it's likely it's using the rotation, and there's a factor of 2 in the rotation P. This is the rotation phase gate. Yeah. And then maybe they do some multiplication on the second loading of the same parameter, but they multiply. This is used in machine learning a lot. Okay. There's also time evolution circuit. So you load a circuit, 3-qubit, you apply Hadamard to the first one, and you say my Hamiltonian is these two, and you evolve this according to this Hamiltonian. Okay, and it's showing that. You could also, so it's the Hamiltonian is sum of the two, so it's just evolve this. Yeah. There's also the quantum volume, so let me not go to the detail of the quantum volume. It's basically estimating how good the circuit is. If you imagine n qubit, and then how deep the circuit you can run. So I think quantum volume is defined as a square, n times n. What is the effective size of the qubit, and then the effective depth. So this is the circuit for you to run that. And there's also arithmetic. You could add bit. For example, you can add you could add 0, 1, 0 to 0, 1, 1 using some arithmetic circuit that they already built. So let me, and then you can actually simulate that, and if what you see that is pi, it's a simple arithmetic. Okay. Okay. Any question on this? This is just strengthening our last lecture's discussion on quantum circuit. Okay, but there are a lot. It's impossible to know everything, so the best thing is go to the documentation. Okay, so what I'm going to do now is going back to the basic algorithm we talk about. Okay, so I covered this part. Right, you can see the documentation. The basic algorithm. Who remember Bernstein-Varzirani algorithm? It's there's a string. A is a binary string. X a set of qubit or bit. A in this here is classical bit. So A dot Z is A1 X1 plus A2 X2 is binary. And okay, here is a single bit. But what you want to do is you want to evaluate this f of x and add the second register. And you want to guess what the bit x is. Remember this is Bernstein-Varzirani. And you can use what we learned from Deutch algorithm, because this is either a constant or a balance, right? A equal to 0 is a constant, A equal to 1 is balance. So you can just use the same method. You input minus state into that second register, and initialize the first qubit in plus state, and measure in the plus minus 1 basis. Okay. My computer is getting slow. Yeah, and recall that when f of x is x, we learned last time is you could use C naught. Okay. And this is how you implement that, right? This is how you implement. If it's constant, then there's no action. Okay, you can generate this to n bit. And essentially you're dealing with each qubit in the first register separately. So you can extract the AI, all these bit information about A. Okay. So maybe what I want you to do is open a notebook. In particular, go back to the Deutch algorithm and maybe think for 5 minutes how you implement this Bernstein-Varzirani. Okay. Now, implementation would be just do the control node, just do this control node. And you could try the first one qubit implementation. But in our Deutch algorithm implementation, we hide this into Oracle. So you may want to have a secret string A, and then you want to hide that, and you want to create an Oracle, and then you want to test whether you get the right result when you do the measurement. Okay, maybe think for 5 minutes, try to think of that. So I will give you the notebook, so I'm not uploading now. I want you to try and think, and then when I give you my implementations or implementation, learn from other places, then you learn more. Okay. I'll be uploading the notebook, but you try to think about it on your own first. Yeah, so we're now implementing a Bernstein-Varzirani, and I want you guys to open the notebook from Deutsch algorithm and try to modify that to make this. So I can show you have the notebook for the Deutsch algorithm. Here's the Deutsch algorithm. So first I have the oracle. So you need to design your oracle. For one qubit, it would be very similar to what I'm doing here. So you would have A, 0. You only have, so here you only have one bit of number. So here you only, your secret function, you will be replaced as secret string, bit string. You have a bit string, or in the one qubit case, one bit case is just a bit. That bit, depending on what the bit is, if it's 0, you don't do anything. If it's 1, you do a control node, right? And that would be your oracle. And this will be the same for the one qubit case, right? and then you verify, do the simulator and verify that you get it all the time, because it's noiseless simulation. You should get what you input it at the secret bits. While you work on that, I'm going to upload the notebook. Yeah. So as I said, this is not just like I'm lecturing. So I want you guys to also work on that. Yeah, and I can work. If you have a question, you can raise your hand. I'll work around. Yeah. Yeah, this one bit case. You can copy this and modify. Just copy, make a copy of that. And here you are not inputting 2, 0, and 1 in the Deutsch. You would input just one bit, and depending on the bit, you change that. And if you're done with one bit, try n bit implementation. You see, this is one. Wait, oh, you're doing the 18 bit. Yeah. Two-qubit is also just extending of one qubit. Right? Mhm. You open the book and you have the slides. It's still showing.
Yeah.
Are you already down?
Oh, that's your code. I
That's
was
my
thinking,
code.
yeah, the scene,
I
right?
already
You guys
upload-
promoted
I already-
right?
I already.
So,
Okay. Okay. Is there any question from Zoom?
No, Professor. But
Okay.
I had this, since we're discussing it, should I go ahead and share how I would implement the Oracle?
If you want, yeah. Why not? Let me stop.
No, I'm not sharing the screen. I just have the idea. I haven't really gone ahead and implemented it.
Yeah.
So we had this homework problem for a Bernstein-Varzirani algorithm back in the previous courses was 568. And the way to go about it was that we introduced a CNOT gate at the instances
Yeah.
where the qubit for the string A
Yeah.
was 1. So
Yeah.
similar to
Yeah.
how the
Yeah.
homework problem is coded, that's how we're going to encode the algorithm.
Yeah.
Insert a CNOT gate at the qubit
Right.
where the value is 1.
Yeah. It's very similar. If you can get the one bit case to work, this could be a homework problem, but yeah, I decided to do it in class. Okay. Okay, good. Yeah. So the TAs are learning along the way. I think I kind of want the format of this course to be like a studio class. Yeah. If you come, then you learn right away. You don't just come here, listen to lecture and not using your brain. You learn the real time. Yeah, in real time. Yeah. And you learn by doing it. And some of you may be very good at programming and also help others. And yeah, I also learn from some of you on the programming side. The 1-bit case is very easy.
Sir, what do you mean by the constant and balance here?
Yeah, so if A is 0, then it's constant, right? Its function is 0, right? 0 times x is 0. And if A is 1, the function is x f of 0 is 0, f of 1 is 1. So it's a balance.
Or
It just,
what about its multi-qubit?
yeah, would also be this half of time there's if A is not 0, then if not a 0 bit string, then it's always a balance. Constant when is 0. So upload maybe upload the solution, but the easy to change Deutsch. I'm not going to. The section will be secret. Okay, you just have one range, and if it's nothing, it's one, right? It's the same. So uh looks like I was kick out Zoom for a few minutes. So what did you guys on Zoom here before I lost my connection?
It was just 1 minute. I think the connection was kind of bad, so that's why you were out.
Yeah. Okay. Let me reshare screen. Okay, as I said, I uploaded Bernstein-Varzirani. Okay, so yeah, you import quantum circuit random because we're going to generate the random bit. Okay, it will be a list. The way I generate it's really similar to the secret function, so I don't need this secret function. I think I just copy from the previous. Okay. So I have this example, I'm going to have a 4 register bit. So I will generate 4 bit that, and I will be given the bit a circuit that number of string 1. I think I'm gonna connect table is my screen. Maybe the one is some problem. Okay. So it's the same as qubit case. If one was seen a bit reg qubit. It's all for very good. You have the circuit, you initialize the first register is that's storing the bit string, the hidden bit string, and you do the Hadamard. You could also use X and then do a Hadamard. Wait, yeah, you could do X and Hadamard. This is a circuit identity, right? See, H is HX. Okay, I do this, and I then append the oracle. Remember the oracle that I have here, it is a circuit. So last time I intentionally turned the circuit into instruction in our Deutch algorithm. Here I did not, so I need to convert that to instruction, then append to the circuit. It's similar to we append these gate, right? And then I measure in X basis by converting to using Hadamard and then measure in the Z basis. And I measure only the first total number minus 1 bit. Okay. Because we only need these so yeah, remember here my classical bit, I don't need to measure the last qubit, so I only have the number of register first qubit in the first register. Okay. Yeah, and this is my Bernstein-Varzirani. Okay, so I hide this. I mean, if you know this gate and you know what's the function. Okay, and so let's just simulate this and then print the count. Okay, the count is 0, 1, 0, 1. So notice that this last bit 1 is this bit here. Okay, Qiskit writing is the least significant one is the Q0, right? So layer labeling is Q3, Q2, Q1, Q0. Okay. And okay, then you compare. Yeah, you compare the secret bit here. Okay, I just go through all the outcome. There's only one outcome. So outcome 0 and have these many count, and the secret bit string is this. Okay. So what you could do is, for example, run this circuit on a fake backend, noisy backend, and see, right? That the fake backend we use in the homework. You can try it, but you need to transpile because we sort of hide this oracle here. But I think it should work because you may need to transpile so that it go back to the gate, and then it can simulate. I have not tried this. Maybe for the noisy backend you have to, but for simulator you don't need to transpile, and it can still work. Well, even I did here. Let me see if I don't do the transpile. This should work. I'll just remove this. Does it? Okay. What does it say? I know. Okay. Yeah. So this is the thing. It does not understand what this oracle is. So even for the simulator, you need to transpile. So this is a feature you need to be aware. You cannot say I want to do this. You need to know how it constructed by circuit, even though we use that as an instruction. So when you really run on a real machine, then you have to transpile. Like transpile. So that means maybe running on the quantum computer using this way, there's no real security because you send this to the server. Server knows what exactly you're computing. Maybe you are running some top secret computation. When you send this, they know the code, they know everything. They plot the circuit, they know exactly what you're doing. But there's actually a way of doing blind quantum computation. You can send instruction to the server and the server to the measurement, but that has to using measurement-based quantum computation, which we covered last semester, but not the blind quantum computation. Okay, so this is the Bernstein-Varzirani. I hope you at least get the 1-qubit case right, because this is really just simple extension to one qubit. Okay. The next one,
Question,
yes.
sir. We run the circuit and we get the secret string, but without the secrets, how could we design the oracle?
Yeah, so oracle would be a computation, right? So without bit string, it's not. Yeah, you need to have some input of classical, right? You need to input of the classical as a bit string so that you can design the oracle. Without bit string, you don't know how to do the oracle.
Yeah, so we need the bit string to design the oracle, but we run the circuit to detect the bit string. So
Yeah.
we knew the bit string initially.
Yeah, so bit string is given to you by somebody else, and somebody else create that oracle and append to your circuit.
Okay.
That makes sense?
Okay.
Yeah. It's just like the Deutch, there's a box here. So he asks, how many times you need to use my circuit to know that the function is balanced or constant? How many times you need to call my oracle?
Yeah, I got it.
Yeah. will be something will be similar in Grover's search algorithm, that we need to know what is the mark item in order to flip a sign, right? But if we put that in the circuit, we know what the item is. Yeah, but it's using the oracle. This algorithm's formula is oracle. Somebody has oracle. You can query the oracle. But global search can be a computation of classical computation that if it's true, then it flip. Yeah.
Can we say we are doing a decryption?
Yeah, in some sense you are right. This is hiding some bit string you're trying to decrypt. It's okay. So let me go. Okay, this is go back to the slides. The next one. Okay, the next one is Simon's algorithm, which is closer to Shor's. Okay, so this we had some discussion maybe last semester on what if the function is not a dot x but actually a plus c. C is an additional register, 1-bit register, 1-bit, and if I have a c, then you will not be able to tell me what x is, because c would flip, would do an extra flip. Well, okay. You can still get x. So in this case, you can still get A, but C will not know. Because C flipped the last bit, minus still get minus. So in order, you can extract A. The Bernstein-Varzirani works, even if you have this, you can extract A. But to get C, you need to run another circuit. To get C, you can just set everything to 0, and then see the last bit get flipped. Yeah. So meaning that to extract both A and C, you need to have 2 use of the oracle. We already circuit. There are some advanced circuits, so maybe not. Let me not do it today. Let's go to Simon's algorithm. Who still remembers Simon's algorithm? This algorithm study harder than Shor's. Because we covered this last semester, but of course, our memory decays, just like quantum computer has a decoherence time. So it's a n-bit and mapped to some finite set. It's a promise problem saying that there's a Hindem string S1, S2, Sn. The functional value of f of x and f of y are the same if the argument differ by this Hindem bit string, and you want to find this bit string. Classically, to find this would be very difficult, exponentially hard. So I'm not going from the beginning to the end, so because you learned this. So let me just remind you some of the things that we need. We need to have Hadamard transformation on n-bit, right? If you have these S bit string doing the Hadamard, it's actually some kind of Fourier transform, but simpler Fourier transform. So you transform this bit information to phase. It become -1 S dot Z. So it's converting the bit information to here. Okay. And if we have a superposition, you add the two together, then you see that there's no amplitude if S dot Z is 1, right? It's easy. S dot Z 1 cancel. So you only get Z that is orthogonal to S. Okay. So that's the key thing. But generally, you will not just get 0 or S, right? Imagine that I run this circuit. I measure the second register to get the functional value. I get some function value, and I would be left with two arguments, x and x plus s. Right? And you do something similar to the previous, it just except that there's an additional x. But the conclusion is that you only get z in this component that are orthogonal to s, orthogonal in the sense of binary inner product. Okay. So to do that is that we're going to run this a few times. Imagine you measure the second register, and then you come back and measure the first register. And the z you get will be orthogonal to s. Okay, so we're going to prepare in superposition for the input in the first register. The second one, assuming that's a 1-bit value, 0, we're in our implementing, we assume that this f of x is 1-bit. It doesn't need to be 1-bit, it can be n-bit. It's just a set. Yeah. Okay. 1-bit would be 2. Yeah, 1-bit would be 2 few to accommodate this. Yeah, so we're not assuming, we assume it's at least the same number to be able to distinguish different pairs. Okay, so this is the algorithm, right? So measure the second register, and it says optional. This is from Nielsen and Trump. And you apply to the first register, measure the first register, you record that value WI because it would be orthogonal to S. Right? But you only did once, you can only get one W bit stream. You do it again, you may get a different W. You could collect enough W, for example, n minus 1 W, then it makes sure that they're different. Then you solve this function to get your S. Yeah, and you output S. Have I uploaded that notebook? So I want to ask, why is not step 4 optional? Can somebody tell me? Because when I argue, I have to measure the second register in order to collapse the first register into a superposition of two things. Why is that optional? Let me upload. Yeah, why is that optional?
Because it only tells us whether the string is even or odd. The parity of the string, yes, that's it. And we only need to measure 0 to n minus 1. That is the first register to obtain the string as.
It's not quite a parity. It is because you imagine you do the measurement, right? And then you will get Z to be orthogonal to that. But doesn't matter what the measurement outcome, you always get S orthogonal to S, right? Doesn't matter what measurement outcome. So that means you don't need to measure. Okay. So now let's take a look of the notebook. You can download it now. So there is a classical part that took me a while to make it right. So this originally, I was referring to a notebook from Circ. Circ is Google's implementation of circuit and simulation, etc. But the classical part, remember, you need to solve the linear equation that's orthogonal to that, and it's binary. So, and it took me a while to fix that because I converted the code to Qiskit. Of course, the classical part's the same, but it didn't work. Somehow the classical part, I mean, I can go to the circ. I have a link in the notebook. So we won't, I mean, so basically I use their function. They have some example function that achieve that. And they also have a classical part. So if you look at the mix circuit, and there's a classical part, post-processing, right? You need to find the solutions, and somehow it's quite tricky because it's binary. I try the code here, is somehow it does not work, and took me a while to make it work. It's not the optimal way. So somebody who is good at Python maybe can improve my code here. So let me go to my code here. Let me close this. So go back to the code. Yeah, you hear it. So we don't have time. Won't go. We can come back next time. So again, I define number of register, and there's some random bit string and this oracle here. So we probably do not have time to discuss the oracle. Okay, it basically is there's a random bit string that want to have the shift, right? And I encode into this oracle. And I basically append this oracle to that. Okay, so I have the register, I have 4-bit. So in order to make sure that I have enough functional value that can be distinct, so I think I'm using also another same number of register qubit in the second register. Okay, and the output, okay, the circuit, you initialize everything in the superposition. This is just for the first register. And you append the oracle, and the oracle will do these computation, right? And then assuming we measure the second register, and in fact we don't need, but yeah, so we don't need to actually measure. So by classical bit, I do not have in this case 2 times the n register. I only have measured the first half. Okay. This find basis is for me to do these classical processing. Okay, so I wrote this part. It's quite ugly, and I need to also use some binary stuff from SymPy. Yeah, this is to do the post processing. To do I find a new space, meaning that the things that are orthogonal to that. Okay, so let me run this before we end. Okay, but you can run the code. You can change the number of bits, etc. Play with that. The tricky part is how you do the post processing, that classical part. Okay, so I run this and I do the simulations. I do the post processing. So you need to make sure. So I have, how many shots do I have? I need to run. You need to make sure you run enough shots. This is the number of samples. Okay, 100 is overkill. Like you have 4-bit, maybe you just run 8 will be enough. Okay, and does it tell me the solutions? Yeah, the solution is there. Okay, because it's noiseless, so I only have one correct solutions. Okay, and this is a bit string that I use. And here we can plot the oracle. Oh, this is, yeah, so this is the oracle. So you see that here, 0 to, well, now I have 5 qubits. Yeah, yeah, because my bit string is 5 bits. Okay. So this is the first register, and this is the second register. It basically is it's copying the value, right? It's basically copying in some way, not necessarily. And then there's also some control, not here. It's the first one is literally copy, and the second one is to disrupt so that you have this here and here. Yeah, if you copy, then it's the same function. So that bit string will be 0. So I have 2 additional disruption. So this is the 2. These 2 are used to scramble that. Yeah, if you just copy one to one, then this bit string will be 0. But according to the secret bit string, I sort of scramble it. Okay. Okay, so maybe you can study the code, and if you can improve the post processing, let me know. And this, you could look up also the circ implementation of post processing. The tricky part is because it's not real number, it's binary, so you have to make sure that you deal with it correctly. Okay, and I wrote some binary Gaussian elimination here, here, line basis. Yeah, you basically just take one row and to see if it can annihilate the other one, and what's left will be can be added to the basis, etc. Yeah. Okay. Any question? So the homework is due on Monday. It's not the hard homework. Yeah, if you can run the code, that means and to get the correct answer, you know you're doing it correctly. Or maybe the DAs should also work on try the homework. I'll give the DA solutions first. Okay. So I guess if you don't have a question, I think that will be it for today. Yeah. Okay. So even though this is going to be recorded, I hope that you attend real time. If you cannot come in person, join Zoom, because it's hard to actively learn by watching video. There's no interactions. Yeah. Okay, so I think, yeah, this is what we end. Simon's algorithm. There are more algorithm, but I have not fully developed the material, so I don't know whether I'll cover. Maybe I should cover Shor's algorithm. Yeah, but definitely we'll talk about Grover's. And there's some linear system. There's more algorithm. Okay. Yeah. So next time we'll talk about Grover. So these are the basic algorithms. Okay, so that's it for today. Yeah. Don't forget to submit homework by Sunday night. Okay. So let me ask, 1 week, is it okay if I give homework like 1 week to finish it? It shouldn't be too difficult. Or I can release the second homework now, so you have more time to work on it. I have all the three, at least I have 4 homework.
I thought the homeworks are already. Oh, maybe.
You are the TA, so you can
Okay,
see the homework that I posted, even if I have not. Yeah. So yeah. So I think we can do more work, like more of these basic homework in the beginning, and then later I would like you guys to read the summer school lab. Those are longer, and then you present in class. Yeah. Just like what I'm doing here, go through the code, go through it slowly, explain. Yeah, discussions. So I'm thinking there are 6 people, at least we can have a pair of 2 students going through one lab book. I think it's reasonable in the sense that they learn that in 10 days and they have to finish 4 lab book for their summer school. Of course, the topic, we'll show the topic next time. But I think this is still the basic, and to some people may be kind of boring because you don't see the applications yet. Once we do more work, homework on that, you help you speed up because the material you already learned that. It's just I'm using the Python, the programming part to show you. So I think maybe the first homework I'll give it every week, and then later we can sort of adjust. Yeah.